ARM's website the other day, and no, it's not, which is the nice part. I think it's this one. Yeah, this is it. Okay. Because it's got a couple of nice things in it that I think will help explain maybe some of the confusion that we've had over like how the stack works and what a few of the instructions do. In particular, it's got some nice diagrams that I think make some stuff a little bit more clear than perhaps my crappy drawing on the board. Um, well, let's just say that they're not going to the Louvre anytime soon either. Okay. Okay, so I'll post this up to Canvas or a link to it because it's kind of handy. But the a couple things about sort of execution, right? As far as we're concerned, um, like the way we've been kind of thinking about each of these instructions is that they're done sequentially. Okay, it fetches an instruction, it decodes it, it executes it. It's also fetching the next instruction, decoding it, executing, and so on. And that's kind of true, but not entirely because um, in the case of sort of modern architectures, there's sort of two layers of several layers of parallelism that are inherent in the architecture. So one of them is that the fact that processors nowadays have multiple cores in them. Okay, so that's one level of parallelism. Although for our purposes, we're not doing any multi-core stuff, so it's as if we're working on single core machines. Okay, so there's that. The second level of parallelism is the fact that each core sometimes actually has multiple units for doing certain common tasks. So, for example, arithmetic, right? So you see here where it says two, it's got integer 0, integer 1, and then two floating point units. So what that means is each core in for this whichever model Cortex processor this is, actually can do two integer computations simultaneously in two separate units. So let's say, for example, that you had, you were adding 5 to register 0, and then the next instruction you were adding 7 to register 1. Well, those two things can happen simultaneously because they don't impact each other, right? And so the scheduler could dispatch those two instructions, one to the integer 0 and the other to the integer 1, and sort of do them in parallel because they don't affect each other. Okay, and similarly on the floating point side. And then the third is pipelining, which again is hard to really see from the level of stuff that we're doing. But the best way to sort of explain what pipelining is how do you guys do laundry? Like, let's say you got 3 loads of laundry to do. Okay, so you put the first one in the washer. Yeah, you put your soap in and quarters or whatever. Do you guys? Oh, you don't have to use quarters anymore. Yeah, you don't do laundry. Buy new clothes. Take it home to mom. Yeah. Okay. Okay. You'd wait for the washer to finish, and then what? Okay, so that's pipelining, right? So what would be a really inefficient way to do 3 loads of laundry? You put the first load in the washer, it washes. You put it in the dryer, it dries, and then you fold it, right? Or hang it up or whatever, right? And then when that entire process is complete, then you put the second load into the washer, okay? But obviously, that's not a very efficient way to do it because what could you do? Yeah, you could be folding what just came out of the dryer while the next load is drying, while the load after that is in the washer. Okay, so that's pipelining. Modern processors have all three of these types of parallelisms, right? You have multiple cores, you have out of order execution, and in some cases, multiple units for of execution. You have pipelining, and depending on the processor, you know, who makes it or whatever, you also have sometimes what's called hyperthreading, where one core can really be running two threads at a time, and it's more like it's got multiple of these units, so it sort of duplicates the commonly used simple things, but without being an entirely different core. And then, right, okay, so, but from our purposes, basically everything's happening single core, no pipelining, and we don't really see the fact that we've got multiple integer units here. Okay, anyway, we've talked about the registers a bunch, and we'll talk about the other ones for the floating point stuff later. Okay, we've talked about the stack pointer and the system registers. And we've talked about the sort of arithmetic instructions, but there's one of them that I want to talk about here because it's going to become important later, which is multiplying, okay? So let's suppose that you want to do, you want to multiply two things, and then you want to add something to the product. There is actually a single instruction for doing that, and it's mad, okay? And there are variations of this that set flags and whatnot too, right? So there is mad s and whatever. So what this does is it does the result of multiplying two things together and then adding the result to them, okay? So now the order here, we have to be a little bit careful, is so notice how in C, like over there on the left, okay, the inputs are in what order? A, comma, B, comma, C. Okay, so according to the calling convention, where does A go? Which register? For the very bottom one. It goes in W0 because it's the first input. Where does B go? W1. Where does C go? W2, okay? Or the equivalent X versions of these, right? Because 32, 64 bits, whatever. Okay, so the syntax here is you're multiplying the first two, so W1 and W0, okay, so that's A and B, and then adding the last thing that's listed. So that's the order that you put them in terms of the assembly. Okay, so this is called fused multiply add. And believe it or not, whenever you do a mul instruction, right, for multiply, it's actually using this instruction, except the W2, what are you adding? It just replaces that with the 0 register, so you add 0 to the result of the product, okay? So the multiply unit actually does fused multiply add. You might ask, why is that useful? But it turns out that can be really handy if you think about things like polynomial evaluation, right? So let me just write up a random polynomial up on the board. So I don't know, I'm just making something up. So 1 plus x squared plus x cubed plus x to the third and so on, right? So if I wanted to evaluate that thing with the computer, what would I do? Well, I'd have to plug in x and raise it to the first, raise it to the second, raise it to the third, raise it to the fourth, do all of those individual things, and then add them all up, right? Or I could be clever. One, two, three, four, 5, 4, 3, 2. No, I only have 4 opens, so 4 closes. I can write it like that. And each one of these things is a fused multiply add, right? Okay. So this method of decomposing a polynomial in order to do the arithmetic with it is called Horner's rule. And it's really clever, right? No, Cade, you're not buying it? Yeah. Well, there'll be an assignment where you'll see the utility of this, okay? Well, because in particular, what's a good use for polynomial evaluation? Yeah, well, yes, okay. Right, but we'll take functions that aren't polynomials, like trig functions, for example. If you want to compute a trig function of some given angle, what do you do? Well, if all you want is a really good approximation to it, what can you do instead? Math majors. Yeah, use a Taylor polynomial. Okay, which of course is really good for small angles, but you know, depending on how many terms you tack on, could be better for other ones. So yes, you could use a Taylor series, or you could use a Chebyshev polynomial, which you guys don't know what that is yet, but we'll talk about them. Okay. So anyway, point being, you can you can accelerate stuff this way. What go in the third register? No, the destination is listed first. So destination is W0. Yeah. But of course, that's the same as W0 and 1, right? Yeah, the destination's always listed first. That's our, yeah, usual convention. Okay. Okay, so good. Now, this multiply add thing will become important a little bit later this morning because I want to talk about sort of how you do modular arithmetic, and that'll be useful for one of the assignments. So, okay. Yeah, so there's that. We'll talk, like I said, more about the multiply and add instruction here in a minute. Okay, floating point stuff, we'll get to that later. Okay, there's also a bunch of bit manipulation operations, and most of these we don't necessarily need, but some of the ones that we do need are things like, okay, we'll talk about extension later when we need it. Let's see. Okay, we've talked about, you know, doing loading immediates. Okay, format conversion, we'll talk about that when we talk about floating point. Basically, you can take integers and round them and so on. And vector data we'll talk about later. Load and store, okay, we've talked about that, but I want to get to the stack stuff. Okay, zero and sign extension, we've kind of talked about those things. Addressing, okay, this is where I really wanted to get to. Okay, so simple addressing would be something like this, right? So this is simple indirect addressing. Load W0 with the contents of the memory cells whose address is sitting in X1. Okay, so that's one layer of indirection. So I go out to X1 and say, hey, there's a number here. That's a memory address. I'm going to go to that, starting at that memory address and load in 32 bits worth of stuff and put whatever I find in W0. Okay, good. But I can also have offset stuff. Okay, so for example here, this would say, all right, go off to X1, treat that number as a memory address, add the offset to it, okay, to get a new memory address, go to that memory address and load something in. Okay, so how did we use this instruction last time? Yes, but keep going. How did we use it specifically? So in our case last time, X1 had a pointer to a what? A string, okay? And what were our offsets? What did the offset do for us? Right, we were trying to do some string processing, okay? And so if we made our pointer to the base of the string, and then the offset would be how far from the beginning of the string we wanted to go. And so in our case, the offset was incrementing by 1 each time, right? So it started at 0, that loaded in the first character, we did something with it. Then we incremented the counter to load in the second character and so on, right? Okay, so here they've just made up the number 12 sort of completely arbitrarily, but if we had a string, for example, we'd be looking at, say, the 13th entry in that string, right? The 0th one being the first one, okay? Okay, now the only exception that's not identical to what's on the screen is when we were doing this with strings, we were loading, to load a single character, what instruction did we use? Yeah, for a single character, what did we have to do? LD R B for byte, okay? Yeah, so this instruction, as it is on the screen, would be loading an entire 32-bit set of stuff. If we wanted to only load an 8-bit, so 1 byte thing, then we would have LDRB for byte, okay? If we wanted to only load in 16 bits for a half word, it'd be LDRH, okay? And if you wanted to load in 32 bits, well, there it is. And 64 bits, we would just replace the W with an X, okay? So it just depends on what size of data we're pulling in, okay? And then remember the rule that Amazon doesn't follow, right? If you're loading in a byte or a half word, which size box do you put them in? The medium box or the large box? They'll fit in both. Always the medium box, okay? Which is what you wish Amazon would do, right? But no, inevitably what happens, you get your, Amazon package, and let's say that, Cole ordered this candy bar in Amazon, from Amazon, a single candy bar. He'd get a box that would hold like 100 of them. Yeah. I'm exaggerating, okay? But actually, Amazon is pretty good at getting the package size just right. Okay, but actually, and if there's anybody listening, I'm going to throw some shade at them. Bath and Body Works, man, their shipping people, it's egregious. Okay, so yeah. Okay, so that's the offset version, right? Base, comma, offset. All right, now there's a specific way that we've used that, okay, which is pre or post indexed, okay? And what this does is you can really think of, okay, where have we used the stuff with the exclamation mark? Yeah, when we want to put things on the stack is where we've done it, okay, but it doesn't have to go onto the stack. It's just that in all of the instance we've used the thing with the version with the exclamation mark, we have been putting things on the stack. Okay, so the exclamation mark does pre-indexing, okay? So what it does is it takes the X1 and the X12, okay, and then so it does two things simultaneously. It does X1 comma 12, right, base plus offset just like before, okay, but the previous version, so if you don't have the exclamation mark, what happens to the result of the computation X1 plus 12? It's discarded. If you put the exclamation mark, it's preserved, and that addition, the result goes back into X1. Okay, so if X1 is replaced with our stack pointer, which is the way we've used this, then we put things on the stack and also change the stack pointer simultaneously. Okay, that's the way we've used it. And it doesn't have to be relative to the stack pointer. It's just that has been in every example we've seen. Okay, so that's pre-indexing. And then the sort of symmetric version of it, of course, we've also used with stack stuff, and that's post-indexing, okay? And the difference here is when the order in which you add, okay? So this one would go out to x1 and retrieve the thing, but then it would add the offset and replace x1. Okay, so it retrieves first from the unshifted version and then modifies the value in x1. Okay, and again, we've used that with the stack relative instruction or stack relative offsets, but it doesn't have to be stack relative. Just again, every example we've used is that. Okay, so when I saw these pictures, I thought, oh, this is really gonna, you guys are gonna love this. Okay, yeah, isn't it awesome? Yeah. Okay. So, well, two things. Stack pointer relative things, right? So when we're pushing and popping stuff onto and off of the stack. Okay. And then also we used it, for example, last time when we were doing string processing, because the pointer is to the base of the string, and if we offset, that moves us to the, character down the line. Okay. 1 byte at a time. If we were storing an array of numbers, for example, our offsets would be, like, let's say we had an array of integers. Okay, how much data, how many bytes is it required to store a single integer? 32-bit integer. 32 bits, okay, so how many bytes? 4. Okay, so if we were going through an array of 32-bit integers, our offsets would be 4 bytes each time instead of 1 byte for characters. Okay, does that make sense? Okay, so your offsets are just whatever size they need to be. In the example we did last time, we were doing string processing, and so it was 1 byte at a time because characters are stored in ASCII, and ASCII is an 8-bit scheme. Okay, now this would be different, of course, if if stuff was stored in Unicode. Okay, Unicode's a bit complicated because actually the number of bits required to store it actually varies. So it's not just that everything is 32 bits. It's that some stuff's 8 bits, some stuff's 16 bits, some stuff's 24, and so on. So it's kind of complicated. But Unicode is nice because, well, what's sort of the problem with ASCII? How many characters can we encode with ASCII with 8 bits? 256, 2 to the 8th, right? That's not a whole lot of things. And it's particularly not a whole lot of things if you're Chinese, right? Okay, and you two would especially know that, right? Because, how many characters are there, written characters in Chinese, the Chinese language? Yeah, it's like thousands of them, right? Whereas how many letters are there in the English alphabet? 26, and okay, maybe 52 if you count the upper and the lowercase separately, which for the purposes of encoding text, you have to. Okay, but point being, on the order of 50 something, okay, maybe on the order of 100 and something if you start talking the Romance languages that have the little accent marks on various letters, right? So Spanish has the N with the little tilde over it. What is that called? No. And what is it? Enye, yeah, okay. And in French, there's the C with the little dangly bit under it. That's called the cedilla, right? Okay, and then there's the accents where you have acute or grave accents on some letters. Yeah, okay. But point being, you throw those in, and you're still well under 200 and something. Okay, yeah. So I mean, and for our purposes, ASCII is enough. So no need to complicate this much more. Okay, so this will hopefully these sort of pictures will kind of help in terms of uh, the the stack management, and of course, there's also the pair version of this, right, which we've used plenty of times. And of course, what that's doing is storing a pair of things at simultaneously to kind of accelerate loading and storing. So, okay, so you've got the load register or store register, and then of course the paired versions of those. So anyway, okay, let me just double check. I think that's it that I wanted to talk. We'll talk about floating point later. It has some stuff in here about branching, and maybe some nice kind of examples to compare C code versus how you would sort of implement this in assembly. And the condition code stuff, we've kind of talked about that, right? How you look at the flags. And then, okay, so the next thing I wanted to talk about would be logical instructions and bit manipulation, okay? So I think we've mentioned the test instruction, and before, okay, which is, so what's the difference between a comparison instruction and a test instruction? So what does compare do between two registers? It subtracts one from the other and then sets the flags appropriately, okay? You would then follow this by a branch instruction that looks at the appropriate flags for whatever type of branch you want to do, less than, greater than, and so on, okay, whichever one you need. Okay, the difference between the comparison and the test instruction, well, there's several. The comparison instruction operates with two registers, right? You're comparing one thing to another. Makes sense. The test instruction operates on a single register, okay? And also on a single bit, okay? So what I'm doing there is with that, or what the example here is doing is this with this test instruction, okay, is it's looking at the bit, well, which bit is it looking at in this case? The far right bit, okay, so it's bit number 0, okay, but what it's doing is it's testing W5 and comparing it against the bit pattern of, in this case, all zeros and a 1 at the end, okay? So that test instruction, what it's really doing is anding, doing a logical bitwise and with the register and a given bit pattern, okay? And what that does then is, because the S is there on the and S, is then sets the flags appropriately, and you could follow that by, like I said, a branch with an appropriate condition code. Branch equal, branch not equal, whatever, okay? All right, so if you want to be able to look at a specific bit, okay, or a specific bit pattern, you could also use the test instruction. And now in this case, what would be the utility of looking at the far right bit, the least significant bit? What does that tell you about a number, an integer? Yeah, it tells you whether it's odd or even, okay? That could be really handy, in particular for the SpongeBob assignment, and I can't believe I just had to say that, okay? How would that be useful in the SpongeBob assignment? Possibly. Well, what is the SpongeBob assignment? Let's start there.
Alternating caps.
Yeah, so you guys know the mocking SpongeBob meme, you know, where he looks like he's a chicken, he's got a beak, and he's like, right? Okay, right. And then the captions for those memes are always in some random kind of alternating lower and uppercase kind of thing, right? And of course, that's gotten used in memes that don't involve SpongeBob and Twitter and you know, so on, right? So it's become a thing, right? And so y'all's job is to basically use scanf to take in a string from the user and then go through and SpongeBob memify it, okay? So not all lowercase, not all uppercase, but sort of some sort of quasi-random alternation between the two. What's probably the easiest thing to do is just to straight alternate, okay? Well, if you're alternating, then the index of which letter you're on in the string is even or odd, right? And maybe you say, okay, I'm going to do odd for uppercase and even leave them alone, or vice versa, whatever. Okay, so does that kind of make sense? All right, so you could use that. Not the only way, but you could. Okay. Okay. Right. So, but then the other thing I wanted to talk about though was the logical instructions. Okay, so we've certainly got arithmetic instructions: add, subtract, multiply. There is also an integer division instruction, and we will use that one later. Um, but you've also got logical and bit manipulation instructions. Okay, so and here, if I had a number, and let me just make up two of them for sake of demonstration. And if I wanted to and these two numbers together, okay, and like I said, I've just made up a random array of bits here. It doesn't mean anything specifically. What does this do? Okay, how do we operate on this? Well, it does it bit by bit. Okay, so what's the far right bit of both numbers in this case? What is 1 and 1? 1, okay. What is 0 and 1? Okay, so it does it bit by bit. Okay, and we've got and here, but of course, what other logical operations are there? Or, XOR, not, NAND, NOR. Okay, so there's all of those guys. Okay, but not necessarily every one of them is implemented in the instruction set. Okay, is that okay? What's sort of the minimal set that you need to kind of do most stuff? If you've got and, or, and not, you can do all the others too as a combination of those. Okay, now XOR is kind of handy, and so it'd be nice if there was an instruction for that. Okay, but point being, you need to be able to do logical instructions, and the test instruction is really just an alias for anding against a given bit pattern. Okay. Um, okay. So, okay, I don't want to talk about conditional select right now. Okay, but point being, you've got and. Let me also show you one other. I think this is the sheet that I want. Nope, that's not it. Here it is. Okay, so this is something that somebody at the University of Washington put together, okay, which is a kind of quick and handy cheat sheet of lots of the common instructions that you might want to use and their syntax and their function, okay? And if you look at some of these, we've used them, right? So we've used add and with carry and add and so on, okay? All right, so fine. But we've also got here logical and move instructions, okay? So some of these we've already talked about, right? Move, move K, move in, move Z, and so on, okay? But the logical instructions that we've got are, well, and, okay? We also have, which one is this? Okay, E-OR. Yes. Yeah. Okay. All right. What is E-OR as opposed to or that's down there at the bottom? Okay. Well, look at the notation there on ORR. Okay, what's the notation? What does the vertical bar mean? Well, we've used that in C. Well, as two vertical bars, but it meant or. Okay, so when we say or like that, we mean inclusive or. Okay, and so what I mean by that, right, is if I ask you, do you have, Caleb, do you have computer science class or film class today? And you would answer, yes. Okay. Now, it happens to be the case that he has both of them today. But he would still answer yes because one or the other was true. Okay. If I asked him, Caleb, do you have computer science X or film class today? Then you would answer no. Okay. Because he happens to have both of them today. All right. And so XOR, exclusive OR, is one or the other, but not both. Okay. Now, in English, and have I gotten on this soapbox before? I know I did in 101. When we say the word or in English, what do we mean? Which one? Inclusive or exclusive? Most of the time, inclusive. Did you eat a cookie or a brownie? Yeah, because, well, maybe you ate both, right? Well, you guys are college students. Right. But if your mom says, would you like a cookie? Would you like cookies or brownies for dessert? And if you say both, she's going to slap you. Exactly. Okay. And if my mom is listening this morning, she might be. I doubt it. Although during the lockdown, uh, when everybody was at home and we were doing everything completely online, she did start tuning into a few of my classes. Um, yeah, and so that was weird. Uh, yeah, hi mom, how's it going? Right. Okay, so yes, so one question. Uh, yes, because if you think about it, and is sort of inclusive by definition, right? You can't say one and the other, but not both, because that's the whole concept of and, right? So yes, you can't have exclusive and. No, because it's not and. Yeah. So um, yeah. Okay. So in this particular instruction set, like instead of writing XOR for exclusive or, they write it EOR, E for exclusive, right? As opposed to X for exclusive, but it means the same thing. Okay, so EOR is the exclusive operation, and then these symbols here, right? This thing looks like a tensor sum, right? Math majors, you guys can, or direct sum, math majors can go nuts with that. Okay, or anybody if you want to really study Boolean algebra, and Farden is uh, doing the old yeah thing. So ah yeah, well, I mean, there's just two types of tensors. Are they covariant or are they contravariant? It's not that big of a deal. Yeah. So okay. So we've got the logical instructions. Is there a not instruction here? Is there a not instruction there to logically negate? Not directly, but could you build it of what we have? Yes. Okay. For example, you can knock something by XORing it or exclusive ORing it against a pattern of all ones. Okay, because anytime you have a 0, what's 0 XOR 1? 1, that flipped it. And if you have two ones, what's 1 XOR 1? That flipped it, right? So you can do it that way. But some of these operations also have a negatable version. So for example, look at EON. What does it do? It does the exclusive OR of not this thing against a given register. So you can also kind of build it like that if you use a throwaway register like the 0 register as one of your operands. Okay, so there's also not NAND or NOR or any of the other ones, right? But that's okay because we can build them out of the things that we've got. Okay, good. All right, now there's a lot of other ones in that pile, namely, so there's ASR, there's LSL, there's LSR, and then there's ROR, and yeah, so what are those guys going to do? Oh, and I'm sorry, there is a negation. Look at MVN, right? That would do it. Okay, so what is ASR, LSL, LSR, and ROR? Okay, what are these guys doing? Well, what are the symbols over there? So look at, like, for example, either LSR or LSL. What's the symbol there? Yeah, but look real closely. It's not smaller than or equal to, it's two of those, right? So what is in C, if I had something like, you know, number two greater than symbols and 1, okay, what does that do to the number? Okay, so let me just pick a value of the number. I'm just going to make something up, right? So let's say num is okay, so let's say I just had the number 5, okay, 0, 1, 0, 1. And then obviously in 32 bits, there'd be a crap load of extra zeros to the left, but I don't need to write those. Okay, so if that's the number, and I do number arrow, arrow 1, what's the result of that operation? Okay, so what did I do to the bits? I shifted them all one unit, one spot to the right. And that's what this 1 tells me, is how many spots I'm shifting. Okay, yes. Ah, yes. Okay, so Farden is noticing, what happened to this 1 who is at the far right? What happened to him? He fell off the boat. He disappeared. And that's the difference between a logical shift and a rotate. Okay, if I had rotated this, he would have come back around to the front. Okay, which is a different operator though in C. Okay, so a logical shift, if something falls off the boat, he falls off the boat. Okay, and you insert zeros as you come from the left. Okay, what is this number, by the way? 2. Okay, so what is doing a shift by one spot to the right tantamount to? What's this equivalent to doing? Hmm? Well, okay, yes, but I mean, in terms of the number 5 and the number 2, what is this sort of equivalent to doing? Not quite, well, yeah, subtracting 3. Smart ass. That's not it, though. Huh? It's division where you discard the remainder. Division by 2, right? Okay. All right, so I know some of you guys have heard this story before, but let's go back to when Dr. McKinney was a young buck in college. Okay. So when I was 19, I feel like this is about to become a Simpsons reference. When I was 17, I drank a very good beer. No. Yeah. Okay. Anyway, so I was 19. I get a job working where? Actually, my mom helped me get this job. Does anybody know? I've mentioned it, I'm sure. It's a department store. Sears? Nope, not Sears. Kohl's. I worked at Kohl's. Okay. I was employee number 1245936. And I still remember that. Okay. Okay. So I'm working at Kohl's one day, and yeah, you know where this is going, right? Because I told this in 101, right? All right. So we're getting close to Christmas season. I mean, there's certainly plenty of Christmas decorations and stuff available for purchase at Walmart. They've been there for months already, which is ridiculous. Okay. So let's just say, when is an acceptable time to start decorating for Christmas? The day after Thanksgiving, no sooner. Okay. And if you are one of those people that do it earlier, you are an abomination.
What if you don't decorate at all?
That's also acceptable. I don't know. Maybe you don't celebrate Christmas. Oh, well, it's taking it down and unplugging it are two different things. Okay, so you could leave the lights attached just as long as you unplug them, right? Okay, so after Christmas, what happens, right, at every store that has Christmassy stuff? Mega sale, because we want it the hell out the door, right? And so the sales get progressively better. The day after Christmas, it's usually like 50% off. A few days later, it's 90% off. Like, we really want it gone. Okay. And so this lady comes up to me and she has an item and she's like, all the Christmas stuff is 90% off, right? I'm like, yes, ma'am. Can you tell me how much this is? Now, to be fair, that could be a challenging question in a retail environment because, right, if they say, oh, it's 25% off, well, how the hell do you know what that is? 25% off of what? Okay, so when in retail, like when they say that, what do they mean? Off of what? What's the starting number for everything? The MSRP, the original price, that's the thing on the barcode, okay, or the sticker or whatever, which nobody ever pays that amount for it, too. That's the other thing, right? Who pays original price? Nobody. Okay. Um, huh? Really? It, well, okay, yeah. If you go and try and buy a RTX 3080 tomorrow, you're going to pay over MSRP. Okay, and maybe for cars too, right? But like you're going and buying a pack of socks, right? Nobody's going to pay above MSRP for that. Okay. And you would, well, I mean, if you're going to be buying new socks every time you want to change socks, right? Then okay, whatever, right? All right, uh, so 90% off of the original price. Okay, so she hands me the item, I find the sticker, and I look at the price, and then what do? Let's say it said that originally was $39.99. Yeah, I just give me that decimal point, $3.99. Here you go. Okay, no big deal. So then she comes back 20 minutes later with a cart full of stuff. And she's like, can you tell me how much all of this is? Yes, ma'am. Because we didn't say no at Kohl's, right? Yes, we can. Um, and so I'm like, 352, what, just burning through these things. And she's like, how are you doing this so fast? You must be really good at math. And I'm like, well, I am a math major, but that's not why I'm so fast at this one. It's because it's 90%, ma'am. Because 90% off means 10% of. Just take that decimal point and move it one spot to the left. Or equivalently, and I didn't say this to her, just shift all the digits one position to the right, but leave the decimal point intact, right? So shifting the digits in arithmetic on your price tag is equivalent to dividing the price by 10, right? Because we use base 10 arithmetic in the real world. All right, so shifting the bits one spot to the right is equivalent to doing what in base 2? Dividing by 2, right? It's the same freaking thing, just a different base, okay? Oh, come on, Evan, you should have remembered this from 101.
I don't remember.
Well, it was also at 8 in the morning. Um, yeah.
Oh, I forgot what specific.
Hmm?
I said learning starts at 9:45.
Learning starts at 9:45. Well, yes, okay, but we can't run a college between the hours of 9:45 and 4 o'clock. Okay, somebody has to teach at 8. Yes.
Does this trick also work for hex?
Yes, it works in any base. Okay. It does also work in octal. Octal? Base 8. Yeah. Why? What did you think I said? Yeah. Well, okay, you've never heard of Octal because nobody uses it anymore, okay? But back in the day on mainframes, so like the PDP-8, for example, you would keep track of numbers in groups of 3 bits instead of groups of 4 bits. And if you keep track of them in groups of 3 bits, then how many things can 3 bits encode? 8 things, okay? And so the system where you only use the digits 0 through 7 is called octal, and it's like hex, but only with 8 instead of 16 things. And it's basically hasn't been used except in the mainframe industry since like the 70s. Okay, so if I ever teach another retro course on like mainframes from the 60s and 70s and stuff, then you guys will learn octal. But it's basically just half of hex. So
Is that more OG than Commodore?
oh, way more OG. Okay, yeah. I mean, and I think I've mentioned this, right? There was a time when there were 0 computers on this campus.
How would you run Crisis today?
How would you run Crisis? There also was no Crisis. Okay, right? In 1832, when Caleb Mills was kneeling in the snow, there were no computers on campus. Oh, hell, there wasn't even a campus. Okay, in 1932, how many computers were on campus? 0. Okay, and if there were, they were people, not machines. Well, that's still true. Well, that's a matter of debate, pardon. It depends on what you define as computer. Um, and depending on how you define it, you could give the crown to the Antikythera mechanism from the 2nd century CE. So about 2,000 years, a little over, under 2,000 years ago. No, it cannot run Crisis. It could tell you when the next solar eclipse would be, but it wasn't going to run Crisis. Okay. Um, so, but it wasn't capable of making a Boolean decision, an if-then kind of statement. So if we define a thing that's capable of doing that as the threshold for being a computer, then the first sort of parts and prototypes and idea would have been Babbage's analytical engine, but he never built the whole thing because the British government cut him off. And that was the mid-19th century. Ada Lovelace worked with him, by the way. You could call Ada Lovelace the first computer programmer to some extent. Okay, So if you mean fully functional and actually worked, then I think you have to give the trophy to Konrad Zuse in Germany, who built several computers out of telephone relays. Okay, so you use telephone relays as the switching element, which nowadays we use obviously transistors. Um, and but he was doing it in Nazi Germany, as opposed to in the West. You know, the ENIAC, for example, would be probably the first. Um, yeah. So yeah. Okay. Well, hashtag liberal arts college. Okay. Okay. So if we do, for example, um, these bit shift operations, right? Those are equivalent to dividing and multiplying by 2. Now, on the division side, you're essentially discarding the remainder if there is any, okay? And there are plenty of instances where that's actually useful, right? And in particular, how many of you guys, when you were programming in Python, right, uh, ever used this operator? Okay, so what does that do? Gives you the remainder upon division by whatever number you put after it, right? So if I put, something percent 2, then that's going to be doing what it will tell me the remainder upon division by 2, not the result of the division, but rather the remainder. If I want the result of the division, I need a different operator. Okay, well, for example, division, right? Or this logical shift. Okay, all right. So where this is going to be useful. Sorry, before I go to there. Well, if we could do logical shift right, can we also do logical shift left? Yes, same idea. It's just going the other direction. Okay. So, for example, if I took the number 5 here and I logical shifted it left by 1 spot, so if I had 0B 0101 and I did left shift by 1 position, then I would get 101, and then I would insert a 0 from the right, uh, in the same way that on the other end, I'm going to be inserting zeros from the left. Okay. All right. Is that okay? Now, there's a variation of this, okay, which is ASR. Okay. ASR, there's no ASL. ASL and LSL are the same thing. Okay. ASR is a little different. Okay. It's an arithmetic shift as opposed to a logical shift. And the difference is this. Let me take a number, and for sake of example, let me just do a 32-bit number. Four, 8, 16, or 4, 8, 12, 16. Okay. As a 32-bit number, that represents -1, right? All ones in binary or FFFFFF in hex. Okay, so if I were to shift this 1 spot to the right, okay, what I would get, so if I did a logical shift left by 1, I would get E. Okay, so if I did a logical shift left, I would insert a 0 from the right, and I would get 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and then a 0 at the end. Okay, or in hex, 7 F's followed by an E. Okay, if I did an arithmetic shift, or I'm sorry, I wanted to do a shift right, not a shift left. I'm sorry, guys. So I meant LSR here. Okay, if I did a logical shift right, what I would get is 0B01 all the way down. And that would be 0xe, no, not E, it'd be 7. Okay, so I'd get that. So what did I insert from the left as I shifted everybody to the right? I inserted a 0. Okay, the logical shift always inserts zeros. Okay, an arithmetic shift, in this case, would actually give me the same number. Okay, and what the arithmetic shift does is the number that I started with here positive or negative?
That would be negative.
It was negative. How do I know it's negative? The far left bit, the most significant bit, if that bit is a 0, what does that indicate? Positive or possibly 0. And if it's a 1, it indicates negative. Okay, so the arithmetic shift replaces, as you insert bits, or you insert a bit, it makes sure it inserts zeros, except in that far left position, it will insert either a 0 or a 1, so that the sign of the result is the same. Okay, so maybe actually, for sake of demonstration, I should do an LSR and ASR by 2, okay, because you won't see the difference otherwise. All right, so if I did this by 2, okay, what would I get? I'd have 2 zeros there. Now that would change the 7 to a 3. Okay, if I ASR by the same amount, then I wouldn't get the same number. I would get, okay, what am I going to have from the far right? So I'd get 0B and a bunch of 1s, okay? But then what's going to be in these two positions? In this position would be a 0. In this position, okay, what would the logical shift have put here? Okay, but what should the arithmetic shift put here? Because the original far left bit was a 1. Okay, and so it preserves the sign of the result. Okay, is that all right? Okay, so now the shifting, right, is tantamount to doing division by 2. What about if you wanted to do division by 10? Okay, in human arithmetic, at Coles, this is really easy. Okay, but from a computer standpoint, how do we have to do this? Okay, so if I wanted to do, for example, let me just take a number, 32 divided by 10. Well, let me just say 1832. Okay, what would I get if I divided this by 10, discarding the remainder? I'd get 183, correct? Okay, so if I wanted to know what this percent 10 is, what is the answer to that? What's the remainder upon division by 10? 2. Okay, what's the quotient? 183. Okay, of course, discarding the remainder. What's the remainder? 2. Okay, let's say I really care about that remainder. In C or Python or whatever, you just use the percent operator and bam, you've got the remainder. So the result of 1832% 10 would be 2. Okay, but what about if you don't have such a machine operation in your instruction set? How can you get the 2? Well, you do the old Texas two-step. Let me write it this way. So you take the quotient, you multiply it by the dividend, and you subtract that from the original number, and what do you get? You get the number 2. Yeah, that's handy. Oh, and if only there were a single instruction for doing a multiply and an add together. Let's call it MAD. Wouldn't that be great if there were a fused multiply add? Oh, that would be. Now do you guys see another reason why it's so useful? The having them fuse, multiply, add? Well, okay, yes, but I could think of that as adding negative 10 times 183, right? Right, addition, subtraction, same thing, right? Uh, and in a demonstration of good comedy routines, what did we start with today? We started with mad. And look where we've ended. Yeah, thank you, Cole. Always got to bring a joyous outlook on class. Okay. Okay. Now, why would this be useful? Well, okay, so after the SpongeBob assignment, what are the two assignments after that? Has anybody looked at them? Okay. String to int and int to string. Okay, so if I write down a number, 1832, as a number, that's a 32-bit or possibly 64-bit, but it's a bit pattern, right? A single bit pattern. What about if I wanted a string that had the character 1, followed by 8, followed by 3, followed by 2? Okay, is there a function in Python or C to do this? Yeah, there are two functions to do this, string to int and int to string, although I think they're called something different in Python. Um, string of whatever just takes a number and makes a string out of it, or you can go the other direction. Well, what would be much more fun to do? That in assembly, okay, where you guys get to figure out how to do it. Okay, so that's what you guys are going to do for those two assignments. Is one of them you will scanf and accept a number from the user as a number and then stringify it. And then the other one, you'll accept a string of digits. Okay, that's, I think I said 19 long or something like that, basically so that we don't have to worry about overflowing a register. And then you'll convert that into a number and print it. Okay, so sort of going both directions. Now, when you're going from int to string, or string to int, what is something though that you might have to worry about? What happens if your user inputs bullshit data? Okay, or in particular, if you go from string to int or int to string, what about if the number is negative? So if I gave you the number negative 1832, what's the string going to have? A character for the minus sign. Right, which means of course you have to figure out how do you tell if the number is negative or not. Yeah? Oh, it's going to be so much fun, guys. Yeah. All right. Have a fantastic rest of your week and bell game if you partake in bell game things. I am not. I'm staying home. Mm, well, it's just recursion.